Yeah, comes on everyone. Let's start off. Last thing we started with optical instruments. Hope everyone has started solving. Like I keep saying, at least finish off 2024 and 2025 questions. If you wait for too long, you will not remember anything. Then it becomes you have to put at least 2 to 3 times more time to revise the stuff again. Not worth it. There. So last class we started with optical instruments. We are done with simple microscope and compound microscope. The next thing is a telescope. So what is the difference between a telescope and a microscope? In case of a microscope, the objects are so small, right? The angle subtended will be small, right? In case of a telescope, the object size is so small because the object is very far. End of the day, in both the things, the question is that only the angle subtended is smaller. When you see through a telescope, you're looking at the sun. Sun is actually very big, but the distance is so large, the angle subtended becomes very small. That is the reason sun and the moon look all of this, almost of the same size, isn't it? Even though we know sun is like infinitely larger than moon, they look the same size because of their distance. So through telescope, we observe distant objects. In a microscope, we see objects which are near, but which are small. So we observe distant objects in case of a telescope. Since the objects are distant, that means the light rays are coming from infinity. So here also, just like compound microscope, we have two lenses, objective and eyepiece. This focal length is Fe, this focal length is F0. Observer standing here near the eyepiece. So light rays are coming from infinity. So this distance will be F0. This will be UE, distance of the object for the eyepiece. So here, if you see, this would be the image height. Now, if you look at this thing, this image would have formed an angle alpha, but finally this person will think the light rays are coming at an angle beta. So here the magnification, so tan alpha is hi by F0. We always take the angles to be small, so that is alpha. Now, even if the angle is bigger, there is no other formula in NCERT. Same thing, we'll stick with this. UV, this is approximately beta. So the magnification is the angle you would have seen with the objective thing. That is alpha. And finally, through the eyepiece, you see beta, which is the final angle beta by alpha, which is F0 by UV. This is the general formula for magnification. Now, in NCERT, we have only one case, but this is a general one. And length of the telescope is nothing but the distance between the lenses, which is F0 plus AB. If you remember, in microscope, we had two cases, normal adjustment and the far point, near point. So here also we have the two cases. This is what is there in NCERT, normal adjustment. So generally at a mains level, whenever they ask questions, it is based on this only. They don't ask the second case until unless they have decided to slaughter you guys. So far point. So what do you mean by far point? Again, I told you why this is important. When you're looking through the telescope and you're observing the sky, you don't want your eyes to be strained. So if you think the final image is at infinity, your eyes will be very relaxed. That means the final rays must be at infinity. That means the eyepiece will think object is at its focus. That means UV is Fe. Therefore, UV must be Fe. So your magnification ka formula becomes minus sign because the image is inverted. Fe, and the length will be UV will be minus Fe. This would be, it's a F naught plus Fe. It is just the magnitude there. This is the main formula you need to remember for telescope. And if you notice something here, to get more magnification, what should be there? F naught must be large and Fe must be small. If you remember in simple microscope, what was the relation? In a compound microscope, for more magnification, which of the following are right? F naught is big, Fe is small, F naught is small, Fe is big, both are small, both are big. Anyone remember? Compound microscope का formula याद है? What was the formula? Length of the microscope into capital D by F naught Fe. NCRT का formula, remember? Both are in the denominator. So in case of a compound microscope, both are small. In a telescope, Fe is large and Fe is small. बस यही question होगा. And these are the questions which scare me actually, because they're easy marks and I worry, like, in case you don't remember, you'll unnecessarily lose marks. The second case is the near point. Like I said, this they mostly shouldn't ask, but just in case. So what's the near point? Again, even I have a difficulty remembering. So if you give me this question randomly, I will derive this. So that's what I'm saying. This thing now, just derive once or twice, you'll get the hang of it. The near point meaning the final image forms at the distance of least vision. So your eyes are maximum strained. So VE is minus D. Magnification is F naught by UV. Using the lens maker formula, 1 by minus D by minus 1 by UV is equal to 1 by FE. Substitute here. This is F naught. If you take out FE common, you end up with 1 plus FE by D. There. This is the magnification in case of the near point. That means the eyepiece will think the image is forming at capital A. Clear with this? But again, they will simply, most of the time I have seen, they ask you the normal adjustment only at a mains level. But I feel you should definitely know these things because, I'm a little suspicious. Advanced when they can frame these questions. They'll put this in a paragraph and they'll ask you. And they're not difficult. It is all based on lenses only. It's not out of the scope. Even at a mains, they can do that. And we can't argue with anything. We can't say it's not there in NCRT. So do have an idea there. And let me show you a few questions how they'll ask. I can understand this thing. There is so much to mug up. These topics are tiring actually. Theory, formulas. Let's go this thing. Look at the first question. I'll just show you one. A small telescope has an objective lens of focal length 144 f naught. Eyepiece is 6 centimeter. Find the magnifying power of the telescope f naught by Fe. Length of the telescope f naught plus Fe. Plus. That is a proper Men's level question. And he said the final image is at infinity. So he's asking for normal adjustment. Have a look at both the questions now. Take a minute. Try to solve and then you see the solution. This is the second one. The diameter of the moon is 3.5 into 10 power 3 kilometers. Earth got distance is given. So we have the moon there. The distance is large, so the angle subtended, let's be theta. This is the diameter and this is smaller. Theta will be d by r. So when you calculate this, that turns out to be 0.09 radians. And magnification we got 40. So which is nothing but theta final by theta initial. That means if you just see with your eye, you will see 0.009 radians. But this telescope will magnify it by 40 times. Theta final will be 40 into 0.009 degrees or 21 degrees. That is the angle subtended by the moon on your eye. So it looks big when you see through a telescope. Clear with this? Again, if you see here alpha beta angle is not small, but approximately we take tan beta is beta only. There is no other way out. Let's see one more. Have a look at this too. First one is clear, straightforward substitution. Second one is that infinity, there's a normal adjustment. Second thing is that far point ka formula, near point ka formula. F naught be Fe by 1 plus Fe by d. This is what I was worried, like they'll pop up something like this and you have no idea how to handle this. Clear with this? So you know your formulas, you'll get the answers. Then these are the differences between a compound microscope and an astronomical telescope. So it is used to increase the visual angle. So both of them are trying to increase the visual angle, but this is for near tiny object. This is increasing visual angle of distinct large objects. Right? The magnification formula is this, LD by F naught by Fe. Here the magnification is F naught by Fe. This is for normal adjustment. In this thing, you decrease the focal length of lenses, both of them. Here you increase the focal length of objective and decrease the focal length of eyepiece. Resolving power is not there in mains, but it can be in something else. So, but this is not, the resolving power is not there in mains portion. Stay with us. Then we have something called a reflecting telescope. Now this is mostly theory. There is no questions or anything. So let's just see that. So whenever you're looking into the space, right, all this Hubble telescope or just James Webb telescope and all, these things just don't take a photograph and, just don't take a photograph. They actually focus their, lenses and all this thing towards one position for a days. They collect a lot of light. They basically take millions of images and then they superpose. And with that, they make their final images. So since the light coming from, the stars is very faint, you need to collect a lot of light. That's the reason if you see these mirrors also, they're pretty large. Something like 7-8 meters ka radius. So you get these huge mirrors. Now, when you take such a large mirror, what will happen? The rays will not be paraxial. So if you use spherical mirrors, you will get errors. So we use parabolic mirrors. Because in case of a parabola, all parallel rays will always meet at the focus. Expensive, but it's worth it. So this will be your objective mirror. So instead of objective lens, we use an objective mirror. So these light rays, which are coming from very far, they're almost parallel. After reflection, they will try to meet at the focus. This is your aperture. So you want as many light rays as possible to enter. Then you put one more mirror here, a secondary mirror. So these light rays will hit and then bounce off into this gap. Mostly try to hit at the focus there. They kind of again become parallel. Then we use a lens. This is your eyepiece. You can become parallel, or they'll actually adjust it such that the image forms at the focus so that you can get a normal adjustment. So what you're looking, you don't look into the sky directly. What you're looking is that image which will form in the secondary mirror. That's what you're observing through the lens. So when you put your eye and you try to look into the space through these big telescopes, you're not looking into the sky directly. So you're looking at something else. This is called a reflecting telescope, and that's it. So there is no questions or anything on this. So you should just have an idea how it is construction and everything working. Okay, so that is one. The next thing, so that with that we're done with the optical instruments. Next part, EM waves. This is another important thing. You get a lot of questions on this. EM waves or the electromagnetic waves. So listen carefully. So in this again we have three parts. EM waves, and second thing is Maxwell equations, and the third thing is polarization. Now, we studied in waves. What is a wave basically? A wave is nothing but propagation of a disturbance, and a disturbance is nothing but change in property at a point. In case of a sound waves, the property that changes is pressure, density, displacement, all this stuff. In case of a waves on a string, the property that changes is the displacement of the points on the string. In case of an electromagnetic waves, the property that changes is oscillating, basically electric and magnetic fields. So when you say I'm looking at light, you're actually looking at the variation of electric and magnetic fields. And who produces this kind of fields? Moving charges. When a charge is moving, it behaves like a current wire, it produces magnetic field. You guys remember Biot-Savart's law variation? Find the magnetic field due to a moving charge. There is a formula. Mu naught by 4 pi q v cross r cap by r square. Check out the notes. There's a Biot-Savart's law variation there. So when you write the equation y is equal to f of x plus or minus vt, this is your general wave equation, right? So the y is a property that changes with x and t. So in EM waves, the property is electric fields and magnetic fields. So when you look at something, you know actually what is happening. So the light which falls on your eyes now, there is something called rods and cones. So whenever you have a time varying magnetic field, it produces a changing magnetic flux. And this changing magnetic field flux will produce an EMF. So these rods and cones, whenever this light falls on your eyes, they actually generate EMF. So every particular frequency of light will have a particular voltage. Random example, let's say red color is 0.061 volts, right? And blue color is, let's say, 0.073 volts, and so on. So it is like you're coded in your brain, this particular voltage when it hits your brain. So this is the color you will perceive. So think of like this, think of a black rose. There, you thought about this. Imagine a blue rose. Thought about this. Imagine a blue color apple. Did you in your life ever saw a blue color apple? Never seen. But there, when I say blue apple, you can think of a pink color donkey. See. So when I say pink donkey, right, the pink color has a particular voltage and your brain is firing that signal. So you can perceive what is pink. So technically, right, now think about it. If you close your eyes and say, think about pink, you can still think of the color. So that means color is something simply it is encoded into your brain as a particular voltage. So if you can actually, and people have noticed this, when people are doing, these brain surgeries, normally when they do an operation on a brain surgery, they don't give you anesthesia because they give anesthesia to only the skull, the skin part, because brains don't have any pain cells, so they don't have pain sensors. So if you poke the brain, there is no pain or nothing. You don't even know someone is poking your brain. So what they do when they're doing the operation, right? They give the anesthesia to the skull, the skin part, so this becomes numb. Then they'll cut it open like a coconut ka thing, right? And then they do whatever surgery is needed, and they put that skull back and they just sew it up, and it gets healed automatically. So normally that's what they do. So when what these people observed, right? When doing surgery and when you put there and they put electrodes and whatever it is, the patients, right, sometimes say like they smell roses even though there are no roses in the operation theater. They can smell things and they can feel things which are not there in the thing. So basically when you activate those particular voltages, you feel that way. Now people who are colorblind, what happens to them? Now some they can't see mostly a red color or something. So basically the red and the blue both are encoded to the same voltage. So you don't have a concept of red. So even if you show them red color, they think it is blue. And if you are colorblind, right, you won't know you're colorblind until you reach a certain age because you will think that is how the world looks. After once you reach a certain age, you will realize people are showing blue and they're calling it red, and you think, what the hell is red? And that is the reason when kids are there, small ones, you should get their eyes checked and all to make sure they're not colorblind. Because they'll grow up thinking there is something called blue. If you see Mark Zuckerberg, he's colorblind. That's why if you see Facebook anytime, it'll all blue only. There is no other color. Notice that he doesn't use any other beautiful color. It's all blue. Instagram, if you see, it has multiple colors. Look at Facebook next time. The name to the heading to the bars, everything is damn blue. Matlab, there's no single color. He's colorblind, so he made everything in blue. So that way. So there is one guy in Europe, right? They found out his same way with hearing also, right? Every sound ka frequency gives a particular voltage. So when you're hearing my voice, you're actually hitting a particular voltages, and that's what you think when I say wave. It hits a particular voltages in your brain, and you can perceive the word wave. Now, this guy, unfortunately, what they realized is neurons which are coming from the ear, they got connected to eyes ka part. They got reversed. So this guy can see sound. Now, I don't know how to think about that. Maybe when you're speaking, he can see colors coming out of your mouth. So yeah, happens. Genetic defects. So if you have a wave which is propagating in one direction, let's say x-axis. Now see, electromagnetic waves are transverse waves. That means the property will change in the perpendicular direction. So when the wave is going forward, the electric fields will oscillate perpendicular to the wave propagation. I'll show you what it means. How does this look? At the same time, you also have magnetic field. But this is also perpendicular to the wave propagation, but E and B are also perpendicular. Think of like this. That means, you're looking straight, right? The wave is going straight. Your left hand is going up and down. Your right hand is going left and right. You're getting how you're walking? You're walking straight like this with your left hand going up and down. And your right hand is going right and left. It's like you're boxing right and left and you're going up and down. So you're doing both at the same time. And you're walking front. So let me show you how that looks. It can be a little confusing, but once you see, you'll understand.
The polarization of light plays a critical role in much of our technology. Challenge classical physics.
Now look at here. Don't look at the whole thing, okay? Choose any one point and look at that one point only. Then we will see the whole thing. So you decide any one point you want. Just look at one point and just look at the pink color and the green color arrow. The pink is the electric field and the green is the magnetic field. So,
classical physics, light can be
if you just observe one point, can you see the electric field is increasing and then is going negative? B is also increasing, then it becomes negative. Just look at one point.
We have two of these Suppose that we...
Did you see that one point? The field at one point is increasing and decreasing. Now look at the whole thing. So since every point the field is increasing and decreasing, it gives you a feeling as if the whole thing is moving. Now look at the whole thing. Can you see the sine wave as if it gives you a feeling the wave is moving?
Suppose that we have two of these electromagnetic space. At each point in space, add like vectors. Into the have two space.
We will talk about this thing later. That is polarization and stuff. But I hope you got the picture how the field varies. So at every point, the electric field and the magnetic field are fluctuating. And the wave is going in the forward direction. Now we have a bunch of formulas. There is no proof or anything. You need to remember them. You get really a lot of good questions on this. So when the wave moves forward, E bar and B bar are perpendicular and they're also mutually perpendicular to each other. So Ey is given by E naught sine kx minus omega t. This is your wave equation if you remember. So Ey is your electric field in y direction. E naught is called peak electric field. X is the direction in which the wave is moving. This omega is 2 pi f, where f is the frequency of light. So when you say the frequency of light is 10 power 10 hertz, what are you actually talking about? You're actually talking about the rate at which the electric field is varying. It is the frequency of the electric field fluctuation. When you say frequency is 100 hertz, that means the electric field is changing 100 times per second. Frequency of light. So now if you remember, in modern physics, we did questions, yeah? A light of electric field, A cos omega t into 1 plus cos omega naught t is incident on this thing. Yeah? Then I told you this is actually made of 3 different electric fields. So the electric field thing was this. Similarly, if you look at BZ, Bz is a magnetic field along z direction. B naught is the peak value. So how do you know which way is the wave traveling? Based on this kx minus omega t. Kx plus omega t meaning left traveling wave. Hope you remember the wave equations. So if you observe here, E bar and B bar are always perpendicular. Now when I say perpendicular, now people think like this. They think if electric field is sine omega t, B must be cos omega t. Don't get confused. I'm not talking about the magnitude. Direction is I cap and j cap. E and B are in phase. Look at that. Both are sine kx minus omega t. That means when E goes to maximum, B also goes to maximum. Perpendicular direction and phase have nothing to do with each other. So when you say in phase, it means E and B increase and decrease together. So when E goes to maximum, B also goes to maximum. There was a question like that in CET. They gave 4 options and they asked something like this. Most people thought E and B will be sine and cos because someone said it is perpendicular. So they thought sine omega t and sine omega t plus 90. Perpendicular vectors doesn't mean the phase angle is 90. So don't get confused. Meaning if you have to write it now, I'll write like this. This is EY, J cap, and this will write K cap. Got it. So this is perpendicular, not the thing. And next thing, obviously EM waves are transverse waves. Omega by K will give you the speed of the wave, in this case C, which is the speed of light. This is important. The peak value of electric field by peak value of magnetic field is speed of light. This we don't have the proof here, so just remember this, very important, comes a lot. Also useful one, units and dimensions. They'll ask you, find the dimensions of magnetic field by electric field. You can do it normally, but will take time. But if you know the result, you get it faster. And next thing, E cross B gives you the direction of wave propagation. So there is a question like this. They said E bar is along minus J cap. Wave is moving along K cap. Find the direction of magnetic field. What do you guys think? So you can clearly see the formula there. E cross B bar is equal to K cap. You are giving E is minus J, so I cross J is K, right? I cross J can be written as minus J cross I. So A cross B is minus A cross B, I cap. Clear? Just bit of a vectors there. There, each point that I wrote is literally like one of the statements there. Then we have something called pointing vector. Again, a lot of new words you will hear. They'll ask you find the dimensions of pointing vector. HSC may they do ask, they'll simply give you which of the following is a point vector. There's a question like that. 1 by mu naught E cross B bar. And you know what are the options? 1 by 2 mu naught E cross B bar, 2 by mu naught E cross B bar, 1 by epsilon E cross B bar, epsilon E cross E bar. Matlab, the thing is, it looks very silly, but if you don't know what is pointing vector, why does it matter, isn't it? You anyway don't know any of the options. So what is pointing vector exactly? This is the energy propagating per unit time per unit area. What is energy per unit time? Power. What is power by area? Intensity. So pointing vector is indirectly intensity of light. That would be easy for you to remember. And this also gives you the direction of light. E cross B gives you the direction of the wave propagation. So if you remember in modern physics, we did something called radiation pressure. Which is 2I by C cos square theta when you're hitting at an angle. So this I is actually pointing vector intensity. So if you see that somewhere, don't get scared. If they write 2S by C, don't think what is that 2S by C. That's a pointing vector, which is intensity. The next one, this is another important one. I showed you this before also. 1 by mu naught epsilon naught is equal to C vacuum. Quite useful. Comes a lot. They also ask in units and dimensions. Find the dimensions of mu naught into epsilon naught. Anyone remember how to find the dimensions of mu naught? Which formula will you use to find dimensions of mu naught? Ahana remembers. Who else remembers? Mu by 4 pi is K. Nere. Yeah. Force per unit length. Force between two parallel wires. Force per unit length is equal to mu naught I1 I2 by 2 pi d. That is one formula where you get everything in terms of mechanical terms, I1 I2, and it's easy to solve. You can find out from other things also, like magnetic field of a solenoid is mu naught Ni, but then B ka dimensions pata hona chahiye. You can play around, you can figure it out. Epsilon is relative permittivity. Remember, mu is permeability. That's an important result there. 1 by mu naught epsilon naught. So if you take it as 1 by mu medium epsilon medium, then this becomes speed of light in medium. Then, and what is mu medium? Mu medium is mu r, mu relative into mu naught. Epsilon medium is epsilon r into epsilon naught. Hope you remember mu r, relative permittivity. This is relative permittivity. Sorry, this is, I wrote relative, okay, my mistake. This is magnetic permeability. This is electric permittivity. That's a mistake. This is a relative permittivity we did recently in the last class. Anyone remember what is the formula? Mu r is 1 plus psi, susceptibility. Yaad aaya? Epsilon r is nothing but dielectric constant. Coulomb's law. So we call it epsilon r, or we call it K in capacitors. It is the same thing. So the refractive index of a slab, so all this stuff is connected to ray optics. Mu refractive index is what? C vacuum by C medium. That is the definition of mu. So this will be 1 by root over mu naught epsilon naught by 1 root over mu m epsilon m. So we get refractive index mu is equal to root over mu relative epsilon relative. Pretty neat formula there. So the refractive index of a medium is the product of mu r and epsilon r ka root. You should definitely remember this. Let me show you how they'll ask a question. Let's say we got a slab whose epsilon r is 5, dielectric constant. You send a light ray at an angle of 60 degrees and it refracts at an angle of 30 degrees. Then they'll ask you what kind of material the slab is made of. Diamagnetic, paramagnetic, ferromagnetic, superconductivity. ऐसा कुछ 4 options they'll make it. Outside is 1. Now from Snell's law, we can do 1 sine 60 is equal to mu of the slab sine 30. So we get mu of the slab is root 3. But we know mu of the slab is root over mu r epsilon r. Epsilon r is 5. So mu r is 3 by 5. Mu r is less than 1. What kind of material is this? Diamagnetic. Suppose if we get mu r is 7, then what kind of metal it is? Paramagnetic. Suppose if we got mu r is 8000, then what kind of metal it is this? Ferromagnetic. Yeah, the result. So that is a general range of the values. That is a ray optics ka question combined with magnetic materials combined with EMFs. Question could be like this. And when they ask you what kind of metal it is, your fuse goes off there. They're like, what the hell are you guys talking about? Clear with this? I'll be taking a lot of tests on this thing. I'll keep some random tests in November and December also. Not every week, I'll keep that test and also I'll just take up only these questions. In some of the speed tests also, we will write only these questions only some days. I'm getting it now. So let's see, we'll work on that. So clear with this? So let's see a few questions on this. I have taken up some PYQs from 2020, 22. I'll send you that also. You can try. So these questions are actually from the JEE. Let's try. Just to brief you, what are the main formulas? E and B are perpendicular. E naught by B naught is C. E cross B will give you the direction of propagation. 3 formulas. ठीक है? E cross B will give the direction. E naught B is C. E and B are perpendicular. Then this one, mu refractive index is root over mu r epsilon r. And 1 by root mu naught epsilon is C vacuum. Total 5 things. Pointing vector is there, but ठीक है. Let's see. Yeah, most of you got it. See. First of all, this is how I would check. This is sine kx plus omega t, so it should be same, 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 same. So there's no difference there. Then E naught by B naught is equal to C. This value here is your B naught, the peak value. So E naught will be 3 into 10 power minus 8. C is 3 into 10 power 8. So that is 9. There is only one option with 9. So D, बस हो गया. और कुछ करना नहीं है. Clear with this? And you can also see J cross K is K cross J is minus I cap. So this is Kx plus omega t. Equation is matching. So that is actual J equation. Huh? Hmm. Hmm. So, yeah, let's see. Again, same thing. So E naught by B naught is C. So this will be 5 into 10 power 8 into 3 into 10 power 8. That gives you 15. So we are stuck with C and D. We need the magnitude. And we know E cross B must be the wave. He said wave is going in Z direction. So that means I'll take it as positive. If it is negative, they would have said minus Z direction. So that is K cap. And B bar is J cap. So this has to be I cap. So C option. Clear? So be careful that minus n will mess up. 15 तो आ ही जाएगा सबको, but then you have to be careful with the directions. Let's see one more. Where we are. Yeah, you can look at the formula there. Speed of medium is given. So mu is C medium by C vacuum, or C vacuum by C medium. Mu always has to be greater than 1. That will give you 3 by 2. But I know mu is nothing but root over mu r epsilon r. And he gave you mu r is 1. So epsilon r is 9 by 4, which is 2.25. Not difficult. If you see these questions now, if you know your formulas, it will take less than 30 seconds. And it's not like everything is easy. You will also have some tough ones like this. Again, in terms of toughness, meaning it is lengthy. Let's see how will you handle this. Now, here, look at the problem here. So we have two electric fields and the charge is also moving. So the thing is, these kind of questions now, you need to realize this electric field will create a magnetic field B1, which is E naught by C. It will be cos kx minus omega t. They'll be in phase. And what about the direction? This is going in I cap. So J cross B bar must be I cap. So that's K cap, isn't it? Got it? Similarly, this guy also will create a magnetic field, which is E naught by C. The function will remain same, cos y minus omega t. But this guy is traveling in J cap. So that will be K cross B bar is J cap. So what is that? I cap, no? So the two electric fields will create two magnetic fields. Then what is the force on a moving charge? Q into the electric field E1 bar plus E2 bar plus Q into V bar cross B1 bar plus B2 bar. Remember this? This is called Lorentz force. याद आया word? Then you have to find that. So that is what he's asking them when he says the net force. Right? So let me show you the full working. There. 0.8, 0.2, B is the answer, yeah. Check it out. So the two electric fields will create two magnetic fields and then you take the net force from there. Clear with this? This would be categorized as tough. So it's a little more working, but most people won't realize like, what is happening to electric fields. Let's see one more. This is also an easy one. Yeah, so again, same story. E naught by B naught is C, but C is 1 by root over mu naught epsilon naught. So E naught must be, B naught must be E naught into root mu naught epsilon. So it's either C or D. E cross B, the wave is traveling omega t minus kx, meaning it's an I cap. E bar is J cap. So this should be K cap. D option. Clear this. This is one type of questions. Now, there is a particular year they asked a question like this, and you don't have anything like this in NCRT. So there is a formula which you need to know. There's a relation between field and this thing. Dou E by dou X is equal to minus dou B by dou T. This always works. And if you actually think about this relation, E by B is equal to C, na? C is dx by dt, isn't it? Kind of. So it comes from that sort. So it's an important relation. So do remember this. Right. So the question was this in the exam. E is equal to E naught sine kx sine omega t. Now, if you remember, this is not a progressive wave. So you can't use all the formulas I taught you now. This is a standing wave. It's a combination of two progressive waves. So here you can't argue E is perpendicular to B and all that thing. Doesn't make sense. So then the question is find B. We are just talking about the magnitudes. And the options were like this. B naught sine kx sine omega t, sine kx cos omega t, cos kx sine omega t, cos kx cos omega t. They made four options like that. There, this result, this equation is given, you have to get B. How will you get it? Try, take a minute. Right. So first what you do, differentiate dou e by dou x. So only x is a variable there. That will be e naught k cos kx. Sine will remain sine omega t. And now you're saying this is minus dou b by dou t. So you're integrating with t. So x will remain constant. This will be integral sine omega t dt. And then you integrate this, you end up with e naught k by omega. That becomes cos kx, cos omega t. Both become cos. Clear with this. And if you remember now what will happen, I'll tell you the problem. You remember me telling you that E and B will be always in phase. So this is sine, this is sine. Now if you blindly remember that, then you will write the answer here as sine kx sine omega t. But that I defined for a progressive wave. So you have to be careful with that. This is a, what do you call it? This is a stationary wave. Suppose if you want to use a general equation, see what happens. Suppose if E naught sine kx minus omega t, if I differentiate this dou e by dou x, what will I get? I'll get E naught k cos kx minus omega t. And when I do dv by dt integrate, this cos again becomes sine. No? So function will come back if you take a progressive wave. But this is not true for a stationary wave. Clear with this? So be careful with that. Take a break, come back in 5 minutes, we'll continue from here. This is a good one, you should know. इसी करने से कम होगा क्या बोल रहे हो कहीं तो लगा So next thing. Now, if you have electric and magnetic fields, then you also have energy. If you remember electric energy density, this we saw in capacitors, which is half epsilon E square. And what is E? Half epsilon E naught square sine square kx minus omega t. Similarly, we have magnetic energy density. One by 2 mu naught B square. We saw this thing in inductors. This will be sine square kx minus omega t. Now, if you use the formula C naught by B naught is equal to C, and 1 by root mu naught epsilon is equal to C, you will notice after simplifying this, half epsilon E naught square is equal to 1 by 2 mu naught B naught square. So what this means, there is a question like this again in CAT. In an electromagnetic wave, what is the ratio of energy contributed by electric and magnetic fields? They're equal. So when you say light is carrying an energy of 1 watt, it means half watt is coming from electric field and half watt is coming from magnetic field. This is also a JEE Mains question. Options were like, E is greater than B, less than B, equal to B, can't say ऐसा कुछ था. To the average energy density, we have to add both of them. Since both are equal, I can write this thing as epsilon E naught square sine square kx minus omega t, or 1 by mu naught B naught square sine square. Basically, the 2 goes off. This is energy density, total energy density. If you want to average energy density, you know what will happen? Sine square becomes half. This itself is a question. What is the average density? Half epsilon E naught square or 1 by 2 mu naught B naught square. So both of them contribute equal. Either you can get electric field or magnetic field. So this is again another one more important formula there. Now this you can modify a bit. Now what is energy density? Energy density is energy per unit volume. So if I take this thing to be half epsilon E naught square, this can be written as volume is A into dx. And if you divide by dt, dE by dt is power by area, which becomes intensity, and dx by dt is the wave speed, which is the speed of light for vacuum or for light. So we get a very interesting formula here. So first time, right, we started noticing these kind of questions in 2015. The intensity is given by half epsilon E naught square C. At least when I saw this for the first time, right, I was like, what the hell are they asking? Let me show you what was the question. Very important one. So the question was, there is a light bulb of power 1 watt. At a distance 2 meters, there is a point A. The question was this: find the peak electric field at point A. Now, just imagine you don't know any of these formulas. The moment you ask find electric field, what will you think? You will think KQ by R square. So you will start searching for the charge. There is no charge. They gave a bulb. And you will like, what are they even asking? मतलब bulb से electric field कहाँ से आएगा? Now, if you know this formula, then you will realize. So what is intensity? Power by area. Which area? The area where the energy is spread out. So 4 pi R square. That is equal to half epsilon E naught square. For electric field, I can also ask you for magnetic field. 1 by 2 mu naught B naught square. That. So whenever you switch on your light, there's actually electric and magnetic fields fluctuating in your room. So they can ask this. They can ask you RMS values. Then what will you write? E peak by root 2. So be careful what is being asked. RMS value or peak value. Clear with this. You can see already, I think we have 7 to 8 formulas. There are a lot in this. So let me show you a question, what they asked. Have a look at this. Again, straightforward formula substitution. So you should know that energy density. This is energy density and not intensity. Is 1 by 2 mu naught B naught square. बस हो गया. So this value is 1.02 into 10 power minus 8. Mu naught का value is 4 pi into 10 power minus 7. This is B naught square. Substitute, get the answer. Unfortunately, you don't have a calculator to use anymore, so you have to solve normally. That was the highlight. Huh? They should have just shut their mouth, right, without telling anything. It's like giving a kid a chocolate and then taking it back. There, this is the EM waves ka first part. So it's all relations between electric field and magnetic field and energy. The second thing is Maxwell equations. Again, these are not new. The first thing is the integral. That's a closed integral. E dot ds is equal to q enclosed by epsilon, Gauss law. The second thing, integral E dot dl. This is the potential difference across a closed loop or EMF in a loop is d phi by dt. Faraday's law of electromagnetic induction. Rate of change of magnetic flux is EMF induced. So basically, this is your EMF and this is your potential difference. If you remember, we did this thing in induced electric field. This comes from EMI. Integral B dot ds is 0 because magnetic fields always form closed loops. This we said in EMI ka introduction mein. Or you can say magnetic monopoles don't exist. The fourth one, integral B dot dl, is mu naught I crossing, Ampere's law. So these 4 equations together are called as Maxwell equations. So Maxwell equations are nothing new. You have done all these things. So now what people found out, this Ampere's law, we had a problem. There is an error. So this is what is important in this modified Ampere's law. The remaining three are fine. So let me tell you what was the actual experiment where they figured out something was wrong. If you take two parallel plates, connect them to a AC source, let the capacitance be C. Distance between the plates is D. And let's say this is V naught sine omega t. Now, because of this, these plates will get charged plus and minus Q, which is oscillating. So we get Q is equal to CV naught sine omega t. And the current I is nothing but dq by dt, which is CV naught omega cos omega t. And because of the charge, you also get electric field between the plates, which is V naught sine omega t potential difference by d. And you can clearly see this is a time varying electric field. So the electric field between the plates is not constant, it is time varying electric field. This is the story. Now then what they did, they took two loops. They took loop 1, they took loop 2 between them. So if you see in loop 1, the electric field is 0, but there is a current passing. The current I is passing through the wire. In loop 2, there is an electric field, but there is no current. So when you try to apply Maxwell equations, loop 1, integral B dot dl. So they calculated the magnetic field manually, they calculated this, and when they equated this to mu crossing, so this value became I. So this B bar is due to the current I, which is flowing in the wire. So, and this I crossing was I, and this was fine. It was matching. There was no problem. Now, when they did this for loop 2, technically speaking, I crossing is 0. Because there's no current between the plates. It's all empty space there. But when they calculated integral B dot dl, they found out this is not equal to 0. They found out there is a magnetic field. So there is a magnetic field being generated. B bar is generated by time varying electric field. So we saw that thing in EM waves. When you have a time varying electric field, it produces a magnetic field. You just can't, electric field just can't exist on its own. ये question था याद है? When you had an electric field, it created a magnetic field. And that's what if you see now, when we started magnetism, I told you E and B are simply two sides of the, different sides of the coin. You cannot have one and you cannot eliminate the other one. Maybe sometimes you can see only one, but the other one will always exist. B is generated by time varying electric field. You didn't have this problem in loop 1 because there was no electric field. That means your Ampere's law, integral B dot dl, is not equal to mu naught I crossing. It didn't work. Now, frankly speaking, it is not the mistake of Ampere, because at that point of time, right, people didn't realize that magnetic field can be created by electric fields. So Ampere's law is valid only for current carrying wires. So this formula, which we generally use, integral B dot dl is equal to mu naught I crossing. This is valid only when E bar is constant. So Ampere thought the electric magnetic field can be created only by current carrying wires. So it worked out. But the moment this thing time varying field came, things got messed up. So because of this, we have to modify the Ampere's law. So how do we take into account that there's an electric field which is creating a magnetic field? So integral B dot dl is equal to mu naught I crossing. So basically this takes care of the magnetic field due to current wires. And we create a new current called displacement current. That's a new terminology. So now in this formula, this B bar is due to current wires and time varying E bar. So this I crossing is the current crossing, which is there if any current is passing through the loop. And the I displacement, this is also called as a pseudo current. It doesn't exist. You cannot measure this with an ammeter or anything. This is just a mathematical correction you created in order to take care of the time varying electric field. Meaning the loop will behave as if there is a current called I displacement flowing in the system, which will give you the answer, which will actually satisfy this is a mathematical correction. So displacement current, you cannot measure. You put an ammeter, it doesn't record or anything. So this displacement current is given by, again, questions are pretty straightforward. Epsilon di electric flux, this is d electric flux by dt. But we know from Gauss law, flux is nothing but q by epsilon. So if you differentiate on both sides, we get epsilon d phi by dt is dq by dt. Then, so someone asks you find the displacement current, just find the charge and differentiate. And you'll actually observe this will be the same current in the wire. I'll show you. Are you getting the story there? So Ampere's law started becoming wrong because we didn't take into account that electric field can also create a magnetic field. So the regular Ampere's law is valid only when you use for current carrying loops. So the actual equation I should use is this. For loop 1, integral b dot dl is equal to mu naught. This is I crossing plus I displacement. So for loop 1, I crossing is I, which is dq by dt, and I displacement is 0. For loop 2, integral b dot dl mu naught, I crossing plus I displacement. I crossing is 0, I displacement is I only. So, finally, how will the whole picture become? The whole situation has become as if this current I which is flowing, somehow it is going in a straight line without, as if there's a wire in the between. Isn't that how the question became? Now see, through loop 2 also there's a current passing through this. If you assume there's a wire. That's why I called it a pseudo current. It doesn't exist, but it plays the role of a current which is passing through the loop. So if someone asks you find what is displacement current, just find the current in the circuit. That is only displacement current. Clear with this? So the whole system behaves as if this current, technically speaking, there should be no current between them, but it feels as if it is just going straight through it and it works. Clear with this? So if at all they want to ask you something really like this, the questions would be of this sort. They will say there are two parallel plates, resistor. Tell me one thing, where do displacement current exist? Meaning if it is there, where is the displacement current? In the wire? Between the plates, isn't it? Displacement current exists between the plates, which is hypothetical though. So we got a capacitor C here. RC discharging circuit, and this is plus Q and this is minus Q. They'll ask you this, find the displacement current. Then the switch is closed, find I displacement. So it's an RC discharging circuit ka formula. Q is equal to Q into e power minus T by RC. Current I in the circuit is minus dq by dt, which is Q by RC e power minus T by RC. बस हो गया. Just find the current, that's the displacement current. Clear with that? So, but the term is important. People, displacement current, they don't understand what it is. So be careful. Because till now, if you see, how many kinds of currents did you heard? Anyone remember? Recently, you heard two more currents: diffusion current, drift current. PN junction में. Drift current is an old one. Diffusion current is a new one. There's a third one: displacement current. Are there any other weird currents? Water current. Nah, that is no. Anything else that you can remember? Think of. I'm getting a feeling there's one more weird one like this. Eddy current. सही है. Eddy current. That comes in which one? EMI. Anything else? RC discharging circuit में current is zero. Seriously. Charge is changing ना रे. Crossing current. No, it depends on where you take loop na Purvaja. If you take loop here, then yeah. If you take loop here, then crossing current is zero. Okay. So let me show you how they framed a question on this also. This was a question. Saturation current, वो भी है, सही है. Photoelectric effect. Total 5 currents we know so far. Let's get this. Yeah, yes, straight formula substitution. So he gave you the displacement current. It is developed within the space between the parallel plate capacitor when voltage is changing at a rate of 10 power 6. The area of the capacitor is this. So what is charge? Q is equal to CV. What is I? dq by dt. Capacitance is constant, which is dV by dt. This becomes I displacement. Capacitance is A epsilon by D. This is d voltage by dt. You know everything here. This is 4.425 into 10 power minus 6. Area 40 centimeter square, 40 into 10 power minus 4. Epsilon 8.85 into 10 power minus 12. Distance d, that's what you want to find. dV by dt 10 power 6. Substitute, solve, you get something. I think this is 4.45, this is 2. The numbers are good. So d will be 4 to, I think it must be 8, I guess. 10 power 6, 10 power minus 12, 10 power minus, yeah, 8 into 10 power minus 3 meters. Clear? Numbers are also good. Got the question? There, again, not tough, but you should know your formulas. So when I say not tough, right, it means like you can solve this within like less than a minute. If you know the data, you can solve these questions in less than a minute. They will save you time in that way. This is the second part of the EM waves, the modified Ampere's law. The third one, polarization. So what is polarization? Now we saw in EM waves, whenever a light travels, you have an electric field which is perpendicular to the propagation. But when I say perpendicular, let's say if light is going in x-axis, every line in YZ plane is perpendicular, isn't it? Any vector in the YZ plane is perpendicular to the I cap. So that means that electric field could be in any direction. So there are infinite electric fields possible. So when a light wave is traveling, it can have multiple electric fields. A light wave with multiple electric fields So generally, when you see sunlight, right, it gives out light in all directions. But if you look at your computer ka screen or your cell phone ka screen, it actually gives you field only in one direction. In more than one plane. Such a thing is called an unpolarized light. So if a wave is going, so you will see the electric field is in multiple directions. Such a light is called unpolarized. Now, in polarized light, so when you say light got polarized, the electric field is only in one direction. So the process of transforming light from unpolarized to polarized is called polarization. So you have field only in one direction. Now, how do you get this polarization done? We use something called Polaroid crystals. Ever heard about this thing? We say Polaroids, your sunglasses. They're actually Polaroid crystals. If you see your TV ka screen or your laptop ka thing, it is a little difficult to see, but if you watch carefully, right, there is a thin layer on top of your TV ka screen. Recently, I think 3 4 months back, it came in news. Some lady went and brought a Samsung ka TV, 44-inch. She thought it was a plastic ka covering and she removed it. So when you do that, TV still works, right? And the entire screen will just look whitish. So you can't see anything. But interestingly, you know what? That film which she removed, now she takes that film and puts on her eye, she can see the screen. So actually, you know what? If you remove the thin film, you make some glasses and you put that sheet now on top of your glasses. So when you wear these glasses, you can see the TV. If you don't wear the glasses, you'll just be a white screen. I'll show you how that looks. It's a pretty thin film, actually. I mean, it's very difficult to remove for normal people. She must be really, what do you call, motivated to actually remove that damn cover. So we call this a polarity crystal. This is how we represent it with an hexagon there, and this is your transmission axis. So what do you mean by transmission axis? So the meaning of this thing is they allow electric field to only go in this direction. I'll show you how it looks. So let me give an analogy. Let's say you have a cardboard, and let's say you make a vertical slit, vertical, and let's say you take a waves on a string. right? And you send a wave. So if you're sending it up and down, what will happen? The wave is also going up and down. The slit is also up and down. It just passes through. But imagine the same thing if you put the cardboard like this and if you make it 90 degrees. Now, if you try to send the transverse wave, it is going up and down, but this will only send you left and right. Nothing comes out. The wave completely gets blocked. Suppose same thing, if you keep a slit at an angle theta, and now if you try to send this, so when this thing hits, you get a wave which will also get slanted at an angle theta. And if this amplitude is A, you get an amplitude A cos theta. So only the component along the slit will pass and the other component will get blocked. Is that making sense? So this is what we call as polarization. Basically, the waves on a string, I think you can understand more clearly. Something similar happens with light also. So any light that tries to pass, only the component along the transmission axis will pass, the other components will get blocked. Clear, Saish? क्या हो गया सैश इतना हैप्पी फील कर रहे हो पोलर क्रिस्टल के बारे में समथिंग हैपेंड क्या ऑल ऑफ यू लाफिंग पोलर क्रिस्टल के बारे में नो ठीक है इट्स गुड टू बी हैप्पी and people smell randomly for no reason. So there are only two possibilities. One, they're either enlightened or they're mad. I will take the first option. So people are enlightened here. JEE ka preparation. So wave thing here. There, look at this picture. This is a better one. Same thing what I showed you. So here, if you see, I'm sending red and blue at the same time. You can clearly see here red gets blocked because it will only send you up and down. Blue will pass through, and if this thing blue will get blocked. If I show you a better picture, there, this is even better. So this is an unpolarized light. You can see the electric field is in multiple directions here. It's like a flower kind of thing. So when this thing passes through the polar right, you can see only the up and down thing comes out. So if you see, right, this is a property of our transverse waves. So this was also a question in the exam. You know, how do you differentiate between a transverse wave and a longitudinal wave? Because if you see, they have all same properties. Both of them create beats. Both of them have, stationary waves. They create every property same. So only transverse wave undergo polarization. Why is that? In a longitudinal wave, how will the particles oscillate? In and out. So if you make a slit, it will always pass through, na? It doesn't matter how you keep the slit, it will always pass through. So only transverse wave undergo polarization. There. That is how you differentiate between a longitudinal and a polarization. This thing. Longitudinal and a transverse wave. So remember, this is quite an important question the last few times. Longitudinal waves do not exhibit polarization. Yeah. So that's a little story there. Now in this, we have actually three formulas. So let's see the first one. This I already showed you with the waves on a string, but let's see it again. This is called Malus law. So if you have a polarized crystal, and let's say this is your transmission axis, let's say making an angle theta. Now, if you send a polarized light, remember electric field is only in one direction, up and down. So this is a polarized light. It's only in one plane, I mean to say. So if you send a polarized light, so you get a light at an angle, right? And let's say this amplitude is A, you get A cos theta. So the component will become an angle theta with the vertical and also become A cos theta. And we know I is proportional to amplitude square. That means if you send an intensity I, you will get intensity I cos square theta. This is what actually happens when you wear sunglasses. When you wear sunglasses, the intensity of the light becomes cos square theta. So the images actually become a little dull. You will be able to see through the light. So the light is still coming from that, but a component of it is gone. And what is theta? Theta is the angle between the transmission axis and the electric field. Clear with this? So this is what happens if you send an polarized light. What happens if you send an unpolarized light? This is the second result you should remember. So if an unpolarized light passes through a polarizer, the intensity becomes half. It doesn't matter how is the transmission axis. So if you're sending this, let's say intensity I, you will get light only in this direction whose intensity becomes I by 2. So if you send unpolarized, you'll get polarized. So whenever you wear sunglasses, the brightness actually becomes half. Why is that? Now you saw from Morris law that the intensity becomes I cos square theta. Now you're sending multiple electric fields, so theta is not constant. For different electric fields, you get different theta. So here theta varies, like 0 to 180 or something. So the average value is cos square theta. So you get half the intensity. Clear with this? So now you tell me, let's say if you have two polarized crystals, this is the transmission axis and this is the transmission axis, both are perpendicular. And if you send an unpolarized light of intensity I, what will I see after the two polarizers? What will this guy see? What is the intensity he will see? Right, nothing, right? So when it goes through this unpolarized, the intensity becomes I by 2. It becomes polarized, right? And then when it goes through this, here theta is 90 degrees. You will see there is no wave. You'll see complete darkness. So now see, if you look into my screen now what I have here is a polarizer basically. You can see this sheet. You'll get it in Amazon if you search. Actually, they're used in this, cameras and everything, Polaroids. So you can see this thing. Now see, you can look at my background, right? It is completely white. If I just put this thing, can you see it becomes kind of little dull? Now, if you see, look at my wall, it's pretty bright in the screen. But if you put the polarizer, you can see it becomes a little dim. The reason the light coming from the wall is polarized, unpolarized. So when I put this screen, only half of the light passes through. Now I will take one more polarizer. So I have two of them, right? Now, if I take both of them and if I keep them, like this, so both of them have the same transmission axis. So you can still see the wall, right? Now, but if I rotate them, becomes completely dark. Nothing passes through. Look at this. If I rotate like this, you can see the wall. You can't see the wall. There, you can see the wall. You can't see the wall. So this thing you'll get it on Amazon. You'll get a big sheet. I cut into 4 pieces. So if you actually take this and put it on your computer screen, now you can see in one direction. You can't see in another direction. Uh, I think let me try to show you that. Now look at this thing. You can see my tab, no? This is my tab where I'm writing actually what you're seeing on the screen. Okay. Now when I keep this thing, I'm keeping the polarizer here. You can see, right? Nothing changed. Can you see in this direction? You can't see anything. I keep it here. You can see the screen. You can't see. So this is clear, the light coming from the screen is actually polarized. So in this 45 degrees, I think this axis is becoming perpendicular. So if I keep it straight, you can see. If I keep it horizontal, you can see. Only in the middle it goes off, see. Is that making sense? So this is what I was saying. Your TV actually has a film like this. And if you remove that, you'll see nothing. So be careful next time you see a cover, don't remove it. So let me show you a few on this. How does that look?
Wondering, is light a transverse or a
So that's just
longitudinal
slinky
wave?
there. You know it. Remember what is the longitudinal wave? So longitudinal wave, the waves are going front and back.
How could we test this?
There, this guy took
This
that
device
slit.
is called a polarizer. It's designed to let waves get through in only one direction.
You can clearly see here the waves only go left and right.
As I send the wave out,
Now see, when he sends like this, everything
it's
passes
getting
through.
fine that way, but this way,
And when you see up and down,
I
it
can't
gets
get the
blocked.
wave through. No
Look
matter
at here.
what
It doesn't
crazy
matter
distance
whatever
I
he does
send,
with the hand. See, the wave always goes left and right.
only the left and right components get through. It's been polarized. Now that only works on transverse waves. These two are
The
crossed.
same thing. So he has taken two polar crystals.
When these two are crossed,
There,
we
you can see
get
complete darkness.
absolute darkness, zero transmittance. But if we cross them the other way,
If you put it in the same axis, you see them.
light still gets through. They're polarizing together the same way.
There. This is what I was showing you. Can't see?
Unpolarized
You
light,
can
for
see.
example, from the sun.
So let's see.
Filters which are and if
Same
you have
thing. He
two
took a smaller pieces.
filters which are perfectly in line, so both vertically, it lets some of the light through, but actually only lets about 50% of that light through. As I start to rotate them, we can see that less and less light gets through, until eventually it's easy to cut down on the glare from
The
reflected light.
sunglasses
Laptop
or even
and
calculators.
screens or things like that filter.
Look at this
Calculators
thing,
is
calculator. We'll
also
show the same thing I
trying to
showed you. You can see
go with that
zero,
filter.
you can't
As I
see
move
zero.
that filter, it basically
So the light
filters
coming
out
from the
that plain
calculator is also
polarized light.
polarized.
And reflected light from water is something else.
Right, so that's a little about polarization there. Clear with this. So let's see a question on this. One more. So if you got this, let's see a question. Let's say we have 3 polarizers. This is a vertical transmission axis. This is like this. This is like this. This is making an angle of 30 degrees. This is making an angle of 60 degrees. If you send unpolarized light, what will you get at the end? What is the final intensity? Get this. If you got this, I think you got it. You got these questions. Here, Aditya. Poroja. Try to Ihan. Nee, Ansh. Nee, Poroja. So first thing, what do you get? You get a polarized light in the vertical direction, intensity I/2. Then when it passes through, what is the angle between E bar and this thing? 30 degrees. So then you'll get in this direction, which is I/2 cos square 30. Now be careful here. The angle between this and this is already 30 degrees. Now what is the angle between E bar and the thing? 30 degrees, na? You're getting it? So this is the angle between E bar and the axis. It is not with the vertical. So I don't care that the transmission axis is making 60 degrees. The field already rotated 30 degrees. So your final answer will be I/2 cos square 30, that is coming through uska cos square 30. I hope that is clear. How much is that? That would be 9I/32. Clear? The first one will make it half, and the second and third will give you cos square 30 and cos square 30. Clear with this? That's a little about polarization. After this, we have a few more things on this. We have polarization and reflection, and we will see different types of polarization. We will do that in the next class on Monday. So another 15-20 minutes, we'll wrap it up, and then we'll start off with, we are still left with diffraction, dispersion. Again, there is a bunch of formulas there, and then we have Wernicke calipers and screw costs. So we should be able to finish off comfortably by Friday. Maybe Friday we will take 1 hour and we'll wrap it up. So Monday when we catch up, we'll continue from here. We will, we'll finish off EM waves, and then maybe we'll finish off with Wernicke calipers or screw costs, because diffraction and dispersion are boring, but can't do anything. We have to do. Okay, so you can start doing EM waves actually. So we have done a substantial amount today. EM waves is one important thing. Every year you get a question on this, and then we also finished optical instruments. So till now we finished semiconductors, bar magnetism, right? Optical instruments and EM waves. So please start doing this. Don't wait for too long, right? Within 1 or 2 days, try to solve. Zyada nahi, at least solve 20 to 30 questions per chapter. Sufficient. You will remember most of it. Then that is one. And second thing, keep a target, try to finish all your PYQs by December 30th. So your job is simple. Keep writing papers, right? And keep solving one material. Finish your PYQs, then do one material, then do one material. So that's how your preparation should go till you're advanced. You're always solving one material parallelly and you're writing papers parallelly.